Karen Kafadar is going to talk about quality metrics.
So I want to echo the previous speakers in thanking the organizers for inviting me here. The level of science in this forensic science workshop is so much higher than you see sometimes in other places. So it's been a real pleasure. I also want to thank all of you for waiting it out to the bitter end here. So thank you very much. I also want to say that I thought that the idea of three experts and two statisticians interleaved, I think that's a really good idea. I don't know if that's gotten as much attention as I think it should, but I think it's a really good idea for process. So I offered this talk, and David thought that it would be all right to talk about quality metrics for pattern evidence. It certainly is a bit different from the other talks that we've heard. And then last night I started analyzing some glass data. So I have to confess I'm going to end up spending about 20 minutes on this one and about 10 minutes on the glass data because that one's more recent. And they're totally separate things. But the objective here of this study, my interest here was recognizing that in the ACE-V process for fingerprint examinations, the A part was this subjectivity, this subjective aspect of looking at the print and deciding, that looks good enough that I can proceed with it. And so I thought, gee, there's so many image quality metrics around there. Wouldn't it make sense to try to do something objective? And so the goal, I was thinking, was that if you had some measure of, say, quality, or I guess there may be a better term is information content. If it could be later correlated with accuracy, in other words, high levels of that would, on average, across many examiners, tend to give a more correct answer, then at least the examiner could go into the courtroom and say, I don't know if I'm right or not, but for prints that have this level of quality, there's a high probability that the call is correct. So I thought at least it would provide some reassurance that, and an objective quality metric that if I did it, or you did it, or somebody else did it, all put into the same algorithm, you'd all get the same number. So that was kind of the idea. The comparison is trying to decide on features. There is apparently a lights out mode in the APHIS systems where they get an objective selection of features. From everything I've heard, first of all, it's proprietary to the vendor, and from everything I've heard, the LPEs, latent print examiners, believe that they do a better job than the algorithms do. I'm not going there, so that's not part of the project. And then the evaluation, there are a number of algorithms. Again, I'm not going there in the verification. I'm simply looking at the first step to see if we can develop an objective measure of quality. The NIST has a NIST IR where they looked at quality metrics for 10 prints, actually, exemplars. This one's going to be for latent prints, we hope. And however, they do just recently, like within the past month or something, develop this NFIQ score for latents. So Cedric Newman showed this plot about a year ago at a workshop. And you see on the x-axis is the number of minutiae, and on the y-axis is the average quality of those minutiae. And then he's got little contours here indicating kind of how accurate the call is if you're in one of those regions. And I said, Cedric, this is it. This is it. This is exactly what I was looking for. This is great. Where are the data on which this is based? Anyone want to guess where the data are? Where they come from? That is correct, Jeff. You are correct. It's experts who sat around and said, well, I think the curves would look something like this. So the idea here is to do something a little more quantitative. So what quality metrics are currently in use? So we spent last year talking to a number of people about that. On what data should these be evaluated for accuracy? Ideally, what you want is ground truth. Okay, we saw Jeff put that finger right there, and then we got his 10-print card. So we know that. This NIST special database SD27A I'm just quoting now from the report, the internal report. The minutiae identified on each image in this database were validated by at least 2 professional latent examiners. Therefore, they should be considered reliable and useful as ground truth for measuring performance. So that's that's a little bit not quite what I had in mind in terms of ground truth. Yeah. Ideally, the latent print came from a truly known source. Now, apparently, the Defense Forensic Science Center outside of Atlanta has some 300 known pairs. We're working on an agreement with the vendors so that they can allow us to use them for these research purposes. It's only 300. If anyone knows of any other data sets, that would be marvelous. So we do need reliable QS pairs. And by the way, there's another value of the quality metric, because we want a range of difficulty, right? How do you define range of difficulty if you don't have a quality metric in the first place? So the quality metric also presumably could be useful for other pattern evidence. But I'm focusing here just on fingerprints because we have more about latent prints than anything else. Will it benefit practice? We certainly hope so. And you know, the performance metrics are going to be to ideally create that database graph showing estimated accuracy, continually monitor the accuracy over time as you get new, known question known pairs, and workflow metrics. If the quality, according to this algorithm or combination of algorithms, is so low, then the lab director should say, don't waste your time, because the chance of being accurate is so low. So there are a few that I will mention here, and if they sound a little bit ad hoc, it's because we really don't have anything where we can put formal procedures, except that at least if we can define them mathematically, we can go through each step and try to assess what would be the variability in each of them. So I'll just mention more about the first two. Hicklin and company have, he works at Nobilis and works with the FBI folks on developing a latent quality assessment software. Apparently it has changed, so I just learned that on Monday from Joanne Buscaglia. And it's, what they do is they get, it was developed by having, the development involved going to experts and saying, look at this print and tell me which regions you think are clear. So mark them as green, yellow, or red. So that it's a little bit self-fulfilling prophecy. And then Neil Jane at Michigan State had some students that I'll just mention a little bit about those. Cedric Newman has one based on pixel quality, also involving the configuration around the specific feature. And also what's good is he takes into account the rarity of the features. He couldn't give us any details about this because I think it was developed with non-disclosure agreements. And then, as I said, the NIST folks have a new NFIQ image quality, fingerprint image quality metric for latent prints. And then Stefan Huckerman works in the area of wavelets, and he and his student are developing a wavelet-based measure of quality. So I was working with Adele Peskin on a measure of cell image quality, and she was tasked with the idea of trying to choose a segmentation algorithm based on edge quality. And the reason is because you wanted to get the cells nicely imaged, and then ultimately, with all these cells, try to identify what kind of cells they are, so that an oncologist would know, for example, if it's a cancerous cell. And then later, tumors do the same idea for the outline of tumors, so that radiologists know where to irradiate the tumor. So she developed these gradient curves by imaging the cells under different conditions and edge qualities. She found that by plotting the absolute value of the gradient versus the pixel intensity, that this curve seemed to have peaks, and that sharper images correspond to sharper peaks. And so she developed a quality metric that involved the gradient and the derivative of the gradient at that peak. And in the top are 4 plots, and the bottom are 3 of these curves. That the one on the left corresponds to 1, 2, and 4 in the plot above. And so the one that was very clear looked like it was either the red curve, the one of the first two, and the one that was blurrier was the one on the right. The second one doesn't correspond to any of those pictures, but the one on the left corresponded to an image with an optimized filter, and the one on the right to a non-optimized filter. So I thought to myself, well, goodness, I wonder if we could apply these ideas to fingerprint images. And so maybe there's something similar here. So I'm going to first show you how it seemed to relate to accuracy, and then I'll describe a little more detail into how it was developed. So what you see on the left is one of these curves like what you saw before. And it's for the lower third of the image, and so you can see that the curve is suggesting that the areas right above it tend to be more clear than the part right in the middle. If you look real closely, it does look a little smushier. And then on the right, again, we're just looking at the lower third. This is the average of the pixels going vertically only over the lower third. And it looks like the part in the, about a third of the way over going across is maybe a little clearer than if you look in the lower right-hand corner. So it looked like maybe there was some hope here. In talking with the latent print examiners, I learned that a number of these features have, they are associated in that if you see an island, you might see a pore not too far away. But also some of these features are more rare than others. So one that's not shown on here is a trifurcation, and apparently I've been told that that's extremely rare. So if you saw a trifurcation. The problem is that sometimes you might look here and you think it's a ridge ending. It really wasn't a ridge ending. If you look at where that ridge ending is, where it's pointing to, if it's quite possible that maybe the print didn't come through clearly there, and actually it's a bifurcation. So that's some of the challenges, I think, in trying to decide on these a quality metric for these features. What you see here is a fingerprint image on the upper left, and then 7 degradations of it. And it turns out that it's really hard to simulate degradation of a print because usually the way it's degraded has to do with whether it's been distorted or smushed in some way. So this is by no means terribly realistic, but we're certainly hoping that the quality metrics associated with the 3 minutiae that have been identified in each of these plots, and you really have to have good eyesight to see this. Let me see, I think it is this the blinker? Yes, that's the blinker. So there's a blue, there's a red, a blue, and a green, a red, a blue, and a green in each of these plots. And the 3 numbers up here are the quality scores for the red, the blue, and the green. And happily, they do decrease. So it looks like we're maybe not too far off. Here's a blow-up of those 3. So you see that's a ridge ending, and then those were 2 bifurcations. That was in the best of the 8 plots, and this is in the worst of the 8 images. So there's the table, and so at least it looks like it's heading in the right direction. And the details of the quality metric are, I don't really have time to do this, but I'm going to say it anyway. The underlying principle is that the gradient intensity between light and dark regions and the overall contrast. So that's what this metric involves, are those 2 pieces, and we're going to multiply them together. So step 1 was to locate the pixel in a small neighborhood of a feature that has the highest gradient, and then look at 10 pixels in that each direction. We did look at different sizes. And then look at the pixels around that feature and compare those pixel intensities. So think about this neighborhood here, and then calculate the gradient, and then look at the set of all possible gradients in that neighborhood and look at the maximum of them. And then the contrast is going to be the largest contrast between that pixel intensity at that point and its immediate 3 by 3 neighborhood. And then just basically, you can see in this second bullet here, we're just going to multiply them. So that metric, by the way, can exceed 100. So there was nothing in here that guaranteed it was between 0 and 100. But out of the 15,000 minutiae in the 273 latent prints in the NIST database, the quality metrics for only about 54 of them exceeded 100. So we're just going to truncate it to 100. As I say, they have categorized the prints as good, bad, and ugly. Henry Swafford has a Dafiki score, which if you thought mine was complicated, this one's even more complicated. It combines 5 measures. But he actually did some tests on same source, which is shown in blue, and a different source, which is shown in red. And based on the number of minutiae, it does look like he's getting fairly good separation in the distributions of these scores. But he's still testing this. I'm going to skip that. I told you a little bit about Hicklin's, and then Anil Jain's group looks at a Fourier analysis kind of metric, and it's print-wide. Trying to actually do a study like this is going to be easier said than done. Trying to identify population of examiners, latent prints. APHIS systems matter, as well as the database to which the APHIS system is hooked up. Plus, we somehow have to convince the lab director to let us populate his database with our 300 known part of the pair. So I don't know how realistic this is going to be, and yet I do feel very strongly that it has to be part of the ordinary workflow, because anything else, you always wonder, did they perform differently than they would have if they were in a real environment. Hopefully it will be double-blind. There was a lot of discussion among examiners about the difficulty of doing that. I think most people in medicine remember that there were tons of discussions about running double-blind clinical trials, and of course they figured out how to do that to great benefit. There would be, probably 2 modes, a lights out versus a not lights out. Type of system, these are the 3 biggest ones. Size of the database, and level of print quality, easy, medium, and hard. And of course that kind of depends on what the value of the metric was itself. It's a I think I've talked about some of those barriers already. So I think one of my biggest challenges right now is to try to think of a mathematical characterization of these quality metrics. Trying to come up with known QS pairs. I don't think, algorithms for realistic distortions, we would still need that. Feasibility study, and identifying latent print examiners who are willing to participate. So the whole logistical study is going to be easier said than done. So I'm going to skip over to the GLASS data, and so if you have questions about the latent print thing, hold on to those, and then I'm going to talk about the GLASS data, and then you can bombard me all at once. And I think I have about 10 minutes. Is that right, Norman? Yes, okay. Let me tell you the motivation for this. And I have to say there's a little bit of a mismatch here, but the motivation is an ASTM standard that has been proposed for the OSAC registry, for looking at different glass samples. So this is kind of related to what James Curran was talking about yesterday. This standard has come up for a vote on the OSAC registry, and the standard talks about a test method using ICP-MS for measuring the concentrations in these elements. So the working hypothesis is that these concentrations develop kind of a signature for the glass that's found at a crime scene. If you found that same signature in glass that was found at a suspect's home, then you might have greater emphasis about stronger feelings about that suspect in this crime. So Section 10 says calculation interpretation of results, and so this is the exact wording, but I'm just going to cut to the chase. So here are the elements that are listed, and what they'll do is they say choose at least 3 measurements of these 10 of these elemental concentrations on the known source fragments. I'm going to call those X's. Calculate those 10 means and those 10 standard deviations, and calculate X bar plus or minus 4 times the standard deviation, which is either 3% of the mean or the actual standard deviation that you calculated, and they're going to call that the match interval. And then calculate 3 more observations, take 3 more measurements on the recovered fragment, and do the same thing. And this is their criterion. If the means of these 10 elements in the recovered fragment do not fall into the match interval for all 10 elements, the glass samples are considered distinguishable. So I was trying to figure out if we had any data that would support this method, and so in my
just one
yeah.
distinction there, which is that there are multiple fragments of glass taken from the control. Then that's step 4. They're actually talking about 3 repeat measurements on a single fragment. And
on a single fragment.
Yeah,
okay.
so they're only comparing a single fragment to the control source at a time. And it's not, it's not immediately clear when you look at that.
Okay, yeah, so you're correct, and the standard didn't make it clear what you do with the results from all of the fragments. Yeah, so thank you for pointing that out. So the first of all, I would say relative standard deviations do make sense. By the way, I'm just going to take logs so that I don't have to keep talking about relative standard deviations. It just makes life so much more comfortable. There are only 3 measurements, which means only 2 degrees of freedom per standard deviation. But it may be, as James just pointed out, maybe they do some pooling across the fragments. This was not addressed in the standard. The minimum SD of 3%, 0.03 on a log scale, may or may not make sense. That's one of the things I wanted to look at, and possible correlation among the elements. So I do have some data, and it turns out that Peter very kindly, I sent this to him, if you can believe it, at 9 o'clock this morning. I said, if you have any problems with my presenting your data, please let me know. And by God, he did. At 11:15, he wrote back. Now, it turns out the technique that he uses is a little bit different than this ICP-MS. So it's not clear to the extent to which some of these results are going to carry over. But nonetheless, I think that it does provide some information. He had 34 fragments from the same source. 33 of them were measured 6 times each on these, it really turns out to be 19 elements. 1 fragment was measured 6 times on 11 consecutive days. So that first one will tell something about the between and with the measurement variability, the between fragment variability, and the between day variability. Then he had a different source. He had 62 samples from 18 manufacturers, and 21 came from Germany, 19 from the US, Japan, 13, and assorted other countries, 9 other samples from many other countries. Of those 21 in Germany, 12 came from 1 manufacturer. Of those 19 in the US, 9 came from 1 manufacturer. So here's some questions. Are the measurement standard deviations of the log concentrations roughly square root of the chi-square on 5 degrees of freedom? We hope so. Not that they have to be, it just kind of makes us feel warm and toasty if they are. Sample number 34 will allow us to look at the between day versus within day variation. Variation on the 33 fragments from the same source. Variation of the fragments from different sources. Looking at the correlation among the elements, I'm so glad we have an honest and bona fide chemist in this audience. And more consistency. Do we see more consistency for samples within country? So here's how I'm going to answer it. I'm going to whip through these QQ plots of the 44 standard deviations of the same samples, the 62 standard deviations of the different samples. I'm going to look at the box plots and the one-way analysis of variance estimates for the standard deviation within day versus the replicate standard deviation. QQ plots and estimates of the standard deviation for different different places, fragments from different countries, different samples. We'll look real quick at the estimate correlation matrix. Remember, we don't have a whole lot of observations here. We're not going to want to go to court with this. And using means of 62 samples in 4 countries, look at those. Okay, so I'm going to whip through these within samples. There are 44 SDs there. They actually don't look too bad, although you will see as I whip through that there are always a couple of outliers. Turns out they tend to be the same one. The one in the upper left is silicone, and they actually use that as a standard, so you're going to always see a boring plot there in the upper left. But otherwise, I was surprised, they actually don't look too bad. Okay, so what I'm going to show you are the root mean square of the 44 samples, the median SD of those 44 samples. If you go back here, if you take 1.0, that might be a rough estimate from that line on the QQ plot of the standard deviation, and then and this is actually the right one, the root mean square, if you have Gaussian data and the recording angel didn't throw any outliers to you. the root mean square from the analysis of variance because it takes into account that you had 11 observations on the one sample. And I'll also report that between fragment SD. And so happily, yeah, look at that. They tend to be less than 3%. So that was really good to see. And between fragments does seem to be a bit higher, but more like about 8 to 10%. Okay, and now what about the between fragment SD to the within fragment SD? Tends to be pretty big, you know, maybe about 2 to 5.5, almost 6. Okay, here are the different samples. You see we're going to see pretty much the same thing, although, you know, a few more outliers in comparison. And those are the same numbers, and in here again we're seeing pretty small standard deviations. I was really pretty pleased. Okay, these are the day-to-day variability. These were the 11 samples. Remember, only 6 observations in each of those boxes, but there does seem to be substantial day-to-day variability. I think all of those F statistics, if you could believe them, with so few observations, turned out to be pretty significant. Here's that correlation matrix. There are too many numbers to look at it this way, so I'm going to cut out the upper diagonal and just put dashes where the ones are, so you can focus on where you can see big ones. So I presume there are reasons why aluminum and titanium might be highly correlated with manganese and things like that. Michael? Don't know. Okay. So again, not a lot of data to go on. These are different countries, and actually this wasn't a surprise that you would see differences within in the countries. Peter did say that the variability within a country is likely to be smaller than you would see in general because they tended to come from the same production in the same plant. Okay, so there they are. And conclusions. This is the last slide. I think I came real close, Norman. 3% relative SD seems fine most of the time. There's substantial variation across fragments, even when they came from the same paint. There does seem to be day-to-day variability. The between-country variation is indeed much higher than the within-country variation. Other variables to consider are manufacturer and color. By the way, those plots where I showed iron were nonsense because it turns out that iron is added to change the color. So really the differences are reflecting color, not iron. It might make sense to model log concentrations as some sort of a heavy tail distribution and think about match intervals from that. I think my biggest concern is over the use of distinguishable. Not distinguishable could imply same source, and I think that's a concern. Okay, that's it.
I have a remark to both speakers. I'm very worried when I hear about objectivity in a domain which is dominated by uncertainty. I would rather speak about standardization. I can know that you can have a standard, but objectivity is something stronger.
Okay, good idea. That's actually a better term. Thank you. Yes?
Just a correction again. I mean, you talked about the number of measurements taken on the control samples. Mm-hmm. There's two stages of measurement being taken there. So you imagine the laser unit goes zap, zap, zap 3 times.
Right.
Those measurements are averaged. Mm-hmm. And then you're averaging over multiple fragments. So there are many more degrees of freedom than 2.
Okay.
So the 3 doesn't actually mean 3 distinct fragments. It's actually 3 replicate measurements which are averaged over.
Okay. So going back to what the actual standard says, and recognize this is an American thing, is that they seem to be talking about each fragment. That's what they're talking about. They don't mention in the standard how you combine results across fragments. Yes?
Would you consider market ratio approach?
Right now I'm just trying to understand the data. Yes, Bill.
Karen, when you talked about quality metrics, it seems like it sounded to me like you were talking about different dimensions of quality.
Yes.
Some of them had to do with the quality of the image itself and the distinctiveness of the lines and so on.
Right.
Others seem to have something to do with the amount of information contained in the image.
Right.
And I'm wondering if there's a need for a different terminology to distinguish those different.
Well, that's a good point. Different terminology. I also think that in whatever is going to be the final metric that we would use, my guess is it's going to be a combination of them for exactly the reason you just pointed out. that some of the algorithms are looking at the image and some of them are looking at more specific details,
And what's in the
features
image,
about the
yeah.
details. That's correct. That's correct. Yeah, we were looking more at the former, and I think Austin and NIST look more at the latter.
Spofford seemed to have some quality of the
Yes,
quantity of information built into it.
right, right. Yeah, he's doing a good job with it.
Thank you very much.
Uh-huh.